All right, in this example, we're going to look at Lesson 8, Long-Term Behavior. This is a due problem from the textbook, problem 1.7.8. And so again, my recommendation is go ahead and pause the video, try to do this on your own. And then if you run into any issues or you want to check your work, then go ahead and listen to the rest. So first thing it says is find the equilibrium values for the model given below by the difference equation. P sub n minus P sub n minus 1 is equal to 0.3 P sub n minus 1 minus 200. And so if we're going to find an equilibrium value, we need to get it into, make this difference equation back into a recursion equation. And so if we want to do a recursion equation, we want to isolate P sub n on the left-hand side. So we're going to add P sub n minus 1 to both sides. And when we do that, what happens is we've got now P sub n is equal to 0.3 P sub n minus 1 minus 200 plus P sub n minus 1. And we've got like terms right here. So we can add these two together and we can get 1.3 P sub n minus 1 minus 200. Right? And so now if we're finding the equilibrium value, we know that there's a formula in the formula reference card to find this that says P star is equal to D over 1 minus A. This is my A parameter. This is my D parameter. So now I'm going to substitute my values into the formula. P star is equal to negative 200 divided by 1 minus 1.3, which is equal to 666.67. All right, now that I've found the equilibrium value, 666.67, let's see what the rest of this question says. Describe the long-term behavior of the model using the initial value P naught equals 100. So let's go ahead and do that. Slide this down. So we've got our recursion equation, which says Pn is equal to 1.3 Pn minus 1 minus 200. P naught is equal to 100. And so we can iterate this. We know P naught's 100, so that means P1 is equal to 1.3 times 100 minus 200, which is equal to, let's see, negative 70. P2 is going to be 1.3 times negative 70 minus 200, which was negative 291. And then P3, 1.3 times negative 291 minus 200, which equals negative 578.3. And so we can think of this graphically. Got 1, 2, and 3. Guess I should shift this down a little bit. P sub n is on our vertical axis, n is on our horizontal axis here. At 0, we started out up here maybe with 100. At 1, we're now at negative 70. At 2, we're at negative 291, much further down. And at 3, we're off the table. Well, keep in mind here that our equilibrium value is way up here at 666. Right? This is 666.67. And so every successive step, we're moving further and further away. So in this case, we would write, we know it's diverging. In fact, we can see that it's moving progressively further away from the equilibrium value in the negative direction. So we could say that the limit of P sub n as n approaches infinity is equal to negative infinity. Right? And so we can also say diverging. Okay. So the next thing we're going to do is look at what if P naught was equal to 100. So again, I'm going to rewrite our recursion equation. P sub n is equal to 1.3 P sub n minus 1 minus 200. P naught is equal to 1,000 now. So we do that, P1 is going to be 1.3 times 1,000 minus 200 equals 1,100. P2 is equal to 1.3 times 1,100 minus 200 which is equal to 1230. And then P3 is going to be 1.3 times 1230 minus 200, which equals 1399. So this time I'm going to draw this graphically again. What we have here is 1, 2, 3. This is n, P sub n. Draw my equilibrium value. That's 666. Started out above it, right? So started out here at 1,000, and after one step I was at 1,100. Second iteration I was at 1,230, and my third iteration I was at 1,400. So I'm doing something that looks like this. You can see now every successive step I'm moving further away from my equilibrium, so that means I'm diverging, and I'm headed off towards infinity, right? As n increases, we would expect that these numbers would just continue to grow. And so if we're going to express this in limit notation, we would write the limit of P sub n as n approaches infinity is equal to positive infinity, and our long-term behavior is diverging.